Heidi-ho, Renaissanceteers, and welcome to Renaissance Puzzle number 86, a particularly peculiar particle. For those of you who have not had a chance to work on the problem yet, or who may not have seen it, I will give the problem statement, and then I'll give a pause so that you may turn off the video and go off and solve it. For those of you who want to see the solution, you just stay on and it will continue afterwards. I hope you enjoy this presentation.
Here is the problem statement. Through some unfathomable series of cosmic events, a particle of material finds itself at the extreme outer region of the solar system, far beyond the orbit of Pluto, but not close enough to any other stars to be significantly affected by their gravity. For a moment, the particle is completely motionless with respect to the Sun, and then the Sun's gravity begins to accelerate it. It falls towards the Sun without coming near any other planets or objects in the solar system until by chance the particle falls down the center of a well on Earth. The quiz question: what time was it when the particle fell down the well? For this problem, assume that the Earth's orbit is circular at a radius of 150 million kilometers from the center of the Sun. Also assume that the particle is not affected by Earth's atmosphere and that the only objects involved are the Sun, Earth, and the particle. There are three levels to the answer: a first-order approximation that can be found rather quickly, a second-order correction that requires a eureka moment, and some third-order corrections that may take a bit of work to quantify. The first-order solution is worth 1/2 point. The second and third order corrections are worth 1 point each.
So now that you've seen the problem statement, if you'd like to solve it, this would be the appropriate time to turn the video off before you see the solution. So I'll give you a moment. Oh, I went down south for to see my gal singing Polly Wolly Doodle all the day. Oh, I'm going to Louisiana for to see my Susiana singing Polly Wolly Doodle all the day. All right, if you're still here, it means you want to see the solution. So here it comes.
Okay, so here we have an oblique view of the Sun with the Earth in its orbit around it. And we know that if a particle falls right down the polar axis of the Sun, it'll never come near the Earth. Likewise, if it comes from this angle, it'll miss the Earth, or from this angle, it'll also miss the Earth entirely. So particles approaching the Sun at these angles do not hit the Earth. We need the particle to approach from the plane of Earth orbit in order to hit the Earth. Also, the particle must be on a line directly to the Sun, and when it strikes the Earth, it has to strike pretty much dead center. So here a particle striking up in the northern hemisphere is not going to satisfy the conditions because it won't get to the bottom of the well. It'll collide with the side wall. So that's no good. Likewise, if it strikes in the southern hemisphere, the same thing. It'll hit the walls of the well before getting to the bottom. So that's no good. So the particle has to come smack dab in the center of the Earth on the opposite side of the Sun. So our first level approximation has it that the particle falls into the well at midnight. Nice and simple. So what's wrong with this model? The problem is that this simple model treats the Earth as a stationary target, just sitting there waiting to get hit. But in fact, the Earth is in orbit with a velocity comparable to that of the particle. So we need to figure out the relative velocities of the Earth and the particle. It is pretty easy to figure out the Earth's orbital speed if you know its distance from the Sun, but in the interest of keeping this explanation short, let's just look it up. Wikipedia says that Earth orbital speed is 29.78 kilometers per second. Now, how about the particle? To figure out the particle velocity, you need to understand escape velocity. Solar escape velocity is the speed at which a mass has enough kinetic energy at a given starting point away from the Sun to completely break away from the Sun's gravity. In other words, the object's kinetic energy must be equal to the energy required to move that object away to infinity. If the object's speed, and hence kinetic energy, is just a tiny bit less than the escape velocity, the object will travel a great distance away from the sun, but will eventually slow down to a stop and fall back towards the sun, regaining the same initial velocity it had when it arrives at the starting point. Since our particle started out at the far fringes of the solar system and fell towards the sun until it collided with the Earth, it had very nearly the solar escape velocity from Earth orbit. We can calculate this velocity using the law of universal gravitation and some calculus, but again, in the interest of expedience, let's look it up. Wikipedia says that solar escape velocity from Earth orbit is 41.1 kilometers per second. So here we have the particle on a direct path to the sun. It is 150 million kilometers away, and so it is approaching the distance of Earth's orbit. The solar escape velocity from a position of Earth orbit is 42.1 kilometers per second. And since the particle fell to this point from the far reaches of the solar system, it has essentially this escape velocity. Traveling perpendicular to the path of the particle is the Earth in its orbit. Earth's orbital velocity is approximated as a straight line perpendicular to the path of the particle at 29.78 kilometers per second. So the ratio of the particle's velocity to Earth's velocity is 42.1 to 29.78, or 1.414 to 1. That's a familiar number. It turns out that it is no coincidence that the ratio of escape velocity to orbital velocity is the square root of 2 to 1. But more about that later. Let's say that prior to collision, the Earth is a distance x away from the collision point. Therefore, at this same moment, the particle is a distance y equal to 1.414x away from the collision point. And if we draw a line from the particle to the center of the Earth, it forms the hypotenuse of a right triangle with angle theta at the particle. Eureka! To an observer on the Earth, the particle appears to travel along the path of this hypotenuse. Therefore, the axis of the well must be on this same line. Not convinced? Perhaps a little animation would help. So here we have the particle and the Earth on a collision course. Let's see that again in super slow-mo. Notice that the particle does not touch the sides of the well. Ta-da! So let's get back to our problem and finish this up. Let's begin by drawing a line from the sun through the center of the Earth, and we will call this our midnight line because it passes through the darkest side of the Earth. And in the new vertice we've just formed, we have the same angle theta that we had by the particle because the two red lines are parallel. And we know that theta is equal to the arctangent of x over y, which is the arctangent of 1 divided by 1.414, which is about 35.3 degrees. Now 24 hours equals 360 degrees of rotation, and the Earth is rotating counterclockwise in this view. So the well is 35.3 degrees past midnight, which is equal to 2.35 hours, which is 2:21:03 a.m. And there you have it. And now we come to our third order corrections. Up till now, we've considered the particle to be on a straight line flight path towards the center of the sun. but Earth's gravity comes into play and causes the particle to deviate from that straight line. This dotted red line is an exaggerated picture of what the deviation would look like. I've done a computer model to simulate this, and the model shows that the deviation from a straight line path is about 1 degree, which equates to about 4 clock minutes added to the time of the collision. I will send the model, which is done on an Excel spreadsheet, in a separate document for those who would like to review it, and I invite you to do your own model if you're so inclined and see what you come up with. Jim Kirk has also done a model, and he likewise has found about a 1 degree deviation, so we're reasonably confident that we're on the right track. And we have one more correction to talk about. And Jim Kirk points out that in addition to Earth's orbital velocity of 29.78 kilometers per second, there is also, because of Earth's rotation, a tangential velocity of 0.46 kilometers per second. This tangential velocity component increases the angle theta by about 1/2 degree, or about 2 clock minutes. So these are the 2 major corrections that we came up with, and you may think of others if you ponder this for a while. So I hope you enjoyed this presentation, and happy Renaissancing!